Hello community! Today we have a look at the comparison of PyTorch 2 with JAX and Flags. So let's start here right now. So we have our torch.nn.Module, the PyTorch base class, meant to encapsulate the behavior specific to the PyTorch models and their components. All other classes here are subclasses to this base class. Now, one important behavior of our torch.nn module is of course registering the parameters. If a particular module class, subclass, has learning weights and all our layers in whatever we construct have learning weights, these weights are expressed as instances of the torch.nn parameter. Now, the parameter class is a subclass of the tensor class with a special behavior. Yes, but I say let's dive into it. So you notice import torch. Then we have here the subclass. We have here class tiny model to our base class. Then we have here the init. Init defines here the layers and all other components of the model. As you can see here, we go with a linear layer with 100 input features, and we have a ReLU activation. We have another second linear layer, and we have a softmax. So then you're familiar with the forward method where the computation happens for our model. So we exactly the same. We have here linear 1, we have our activation, we have our linear 2, and we have our softmax functionality. Beautiful. Then we say, okay, we take our tiny model, and now we look at the model itself. Then we just look at one layer of the model, the second layer. Then we look at the model parameters. Clear output. We look at the model parameters, and then we looked here at the parameters for the second linear layer in particular. So let's have a look here. Where are we? We are here. So at first the model. Model, as I told you, we called it tiny model. It has linear layer activation ReLU, linear layer softmax. Beautiful. If we look at one layer and take the second layer, we have a linear layer, we have input features from 200 and the output features of a class of 10. Now, if we look now at the complete model parameters, remember we have two layers, so we have now the parameters. The parameters for a linear layer, of course, are our weights and our bias. So the first tensor here is the weights from the first linear layer, from the dense layer. And the second tensor here is simply our bias. Then we have another layer, as I told you here. We have now our second layer, the weights, and of course our bias. Now if you look then at particular the layer parameters for the linear layer number 2, you will see this is exactly what I just showed you. Just compare here these two numbers. Yes, beautiful, they are identical. So to make it really simple, the simplest thing is just a single linear layer. So we have here a linear layer with 3 input parameters and 2 output. We take here some random torch and we look at the input. We look at the weights and the bias parameter and at the output. You're not going to believe it, exactly what we expect. This is our input tensor. Then we have here our parameter, and this here is out first our weight. Our weight parameter is here at first, and then the second one is our bias parameter. Great, and output, of course, is calculated. Beautiful. So, whenever you do the matrix multiplication of x with the linear weights weight, the W, so W times x plus b, and we add the biases, you know, this is the output vector of a linear function, and we call this output y. Beautiful. Now, please note we have autograd. This is beautiful now in PyTorch 2. One other important feature to note, when we check the weights of our layer with lin weight, it reported itself as a parameter, which is a subclass of the tensor, now you know it, and let us know that it's tracking gradients with autograd. This is now the default behavior, and this is so beautiful. You see, PyTorch 2 also now borrows a little bit from JAX, Flags. It's more than 3 years old. So you see, we have now this beautiful acceleration points here, also in PyTorch 2. Linear layers are in deep learning models, yes, you know. Yes, we have now a torch JIT script. The torch, this is, yeah, and if you have parallelization, yes. But let's look at a very simple example. In PyTorch, let's look at regression. So we take here, remember the California housing market. where each house has 8 characteristics, the size of the bathroom, the size of the bedroom, and whatever. And we want to find the price. A single numerical value should be the output of our model. So what we do, we split it here into training and the testing data set. We have here a PyTorch model, we have a sequential container, yes, yes, yes. And yeah, just dive into this. And then sequential, so we have a linear layer, we have 8 input parameters. These are our 8 elements from our CSV file. And we have, as you can see here at the end, we have 1 output parameter. This is exactly the price of our house according to a regression model. And as you can see, our structure is simple. We have a linear layer with a ReLU, another linear with a ReLU, another linear. Beautiful. So what we do now is we calculate the loss function. We use here the mean square error functionality. And as an optimizer, we take the classical atom. Beautiful. So my number of epochs is 20. My batch size is 128 default. And then we start our training loop. And here you see it here, model.train. This is classical what we do in PyTorch. And we have here our batch start, yes. So the first one, you notice, is the forward pass. So we're making prediction. We predict Y with a forward pass. And then we calculate the loss between the original and the predicted data point Y. This is our loss function here. And then we start with the backward pass. For the backward pass, at first, maybe for the optimizer, you have to set all gradients to 0, that they do not accumulate. But the backward pass in itself here is for computing the gradients of the loss with respect to the learnable parameters. You notice loss.backward. And then comes the beautiful step where you update now your parameters. And remember, the parameters in our model, in our layer, are the weights and the biases. So optimizer.step. You can evaluate this. Yes, so beautiful that I just show you that it runs. Where are we? Yeah, this is our model, as I told you. Linear with ReLU functionality. Epochs, I think I set epochs to 20. You see our mean square error from 25 goes down 3, 2, 1 point. Oops. Yeah, so you see here, this is the mean square error goes down as we expected. So the model is working. So this is our typical way how we do it. We have here the backward. We have here, yes, set the rear, and then we loss function. Beautiful. This is what you know, and this is what you love. Now, if we look at this now let's make it a little bit smaller. Now there's one sentence that shows you immediately why it's not working. Since in JAX we do functional programming, which calculate the gradients via function transformation, we do not have function like backward. We do not have optimizer step like here. This does not exist in JAX and Flags. So you see, those functions here are really the breaking point where we say, hey, we do not have the data here, like here, where we can have the data in our objects. We're doing here on JAX and Flags, here on the left side, we're doing functional programming. And you might ask, so where are the data? Hey, this is a good question, and this is exactly where now the video starts about JAX and Flags. So how do we do this? How we do stateful computation in JAX when JAX is, per definition, a functional programming framework? So we have here an author, Vladimir Mikolik, beautiful Colab. I leave you the link to this Colab in the description, and he comes up with the solution in a very nice way. So in machine learning, program state most often comes in the form of the model parameters, the optimizer state, some stateful layers itself. So how do we find a solution to this problem? So some JAX transformation, most notably the JIT command, just-in-time command, impose constraints of the function they transform. Must have no side effects. This is what I already showed you. This is because any such side effect would only be executed once when the Python version of the function is run during the compilation. So how do we do this? Now, there is an easy example. So it's called a counter. So we just look at a simple stateful program. And yes, we can write stateful program also in JAX, as you can see here. So we have a simple counter. We have here our class. We call it counter. So we have here the count and a reset function defined. Beautiful. So if we, oh yeah, maybe it's a good idea to clear all outputs. So if we run here the stateful program, please remember this is a stateful program. So we get for arranged, yeah, let's do 5. We get 1, 2, 3, 4, 5. This is exactly what we were looking for. Beautiful. So how do we do this now if we have here now the JIT command? The n attribute maintains the counter state. So where's our n attribute? Our n attribute is here. Increments the counter and returns a new value. So we have here n plus equal 1. Okay, so you say beautiful. So the n attribute maintains the counter state between successful calls of count. It is modified as a side effect of calling count. Now, let's say we want to count fast, so we have JAX JIT in the count method. So we just put in JAX JIT without taking care about anything else. And you will see, oh, it does not work. We get 1, 1, 1. So why is this happening? This is because here our line n plus equal 1, as I showed you here, it's only run once. And if it's only called once when JAX compiles the method call. So moreover, since the return value doesn't depend on the argument to count, once it returns the first one, subsequent call or fast count will always return 1. So this won't do. So how do we fix it? The solution to the problem, explicit state. So I show you here this on a counter beautifully. So you will see it is rather easy. Now, part of the problem with our counter was that the return value didn't depend on the argument, meaning there was a constant somewhere baked into this compiled output. But it shouldn't be a constant. It should depend only on the state. So how do we do this? How do we encounter this? So again, we have now a class counter version 2. So you can see here now in our function count here, in this new version of counter, we moved n to be an argument of count. So we have here now n, an argument of count, and added another return value that represents the new updated state. So beautiful. To use this counter, we need now to keep track of the state explicitly. But in return, we can now safely JAX JIT this counter. So let's see if this is true. Let's run this here. So as you can see here, we get here from count, here the counter state and the counter state. As they told, hey, we just need to return n plus 1, but we want to separate its role as the output and as the counter state for deductive purposes. So we get n plus 1 and n plus 1 and n plus 1. So you get it, beautiful, it works. But now let's have a look if it's also working if we JIT compile it. And yeah, unbelievable, it is working now with JAX JIT. So this is great. This is exactly what we wanted. And now we can find a general rule or a general strategy from stateful to stateless. So we apply now the same process to any stateful method to convert it to a stateless method. So you have here the class, the stateful class. You have here some state. And then you have here stateful method. Beautiful. And you want to transform this now for JAX in a stateless class. So we define our class stateless, where we have the stateless method. And now state is here, an argument of our stateless method. This is a common functional programming pattern and essentially is the way that state is handled in all JAX program. Now, isn't this nice? Notice that the need for the class becomes less clear once we have rewritten it away. Yes, yes, yes. Yes, yes, yes. So let's do a simple example. I think examples are always great. Linear regression. Linear regression with a gradient descent. So let's have a look at this. Here we only deal with one kind of state, and this is the model parameters, the weights and the bias of our model. But in general, we'll see many kinds of state being threaded in and out of JAX functions, like an optimizer state. We will neglect an optimizer for the moment. We will neglect any batch normalization for the moment. Just want to show you an easy example. So what we do, we have here our class of parameters, and we have the weights and the tuples. And those are JAX NumPy arrays. Great. Then we have the initialization of our parameters. And as you can see here, we have our, in general, our keys. So we have our weights and our bias. So we return the parameters, our weights and our bias. And then, you're not going to believe it, we have our loss function here. So compute the least square error of the model prediction on X against Y. Beautiful. You have defined a learning rate, whatever you like. And then we have here our update function. This is now the most important function. So performs one stochastic gradient descent update step on parameters using the given data. So here we have now JAX grad on the loss function with our parameters. As I told you, no optimizer state, just make it easy. And now you already see what's going to happen. We have a JAX tree map. So a typical map, but here we go for a multi-input function over a PyTree arguments to produce a new PyTree. And as you can see, this is exactly what we're going to talk next time here, PyTrees, data structures. But for the moment, let's just accept this. If you want to see what a JAX tree utility tree map does, kind of a lambda function, you have here x plus 1, and then you have here your dictionary with x and y. And if we execute this, you see x plus 1. So 7 becomes 8, 42 becomes 43. And the same is, of course, true here if we calculate this little demo program. Now, as I told you, our random number generation differs now from NumPy in JAX. And the reason is that NumPy's design makes it hard to simultaneously guarantee a number of desirable products for JAX, since in JAX it must be reproducible, parallelizable, and vectorizable. So beautiful. We know here split is now a deterministic function that converts one key into several, normally 2 independent keys, and we keep one of the outputs as the new key and can safely use the unique extra key as input into a random function. This is exactly what we're going to do here. We have here now 42 for seed, for example. This here is now for our true weights is 2. For a true bias, we say -1 for our linear functionality. So in order to generate different independent samples, we split the key. And we have here now JAX random split. And we get now here a primary key and a sub key. I show you here what it is. And then we just have defined our x, 128x parameters. And now we just need here the y coordinates exactly for a linear transformation. So we say here, we take our x coordinates times the weight plus the bias plus some random noise. Beautiful. And then here it goes. We fit now our regression function. And this is exactly our update function we defined a little bit before. And we plot it so we see how good it fits now a linear transformation. And if you look at it, you see exactly this is here now our linear function. And the blue dots show you now here our 128 x and y coordinates, where we have in y a little bit of noise. But you see, beautiful, you can clearly see there is a relation between those two data sets. And now you might ask, okay, this was in the simplest version. So if we now have any other jittered JAX program that must handle state, handling parameters naturally seems fine if you're doing just with 2 parameters, 2 weights and the bias. But if you have a neural net with dozens of layers, and how do you want to do this? Do you want to manually go now to dozens of layers? And the good answer is no. We are not supposed to initialize them all manually, especially repeating what already written in the forward pass definition. And I will show you now in the next video in flags how we do this. And are we supposed to pipe all these things around manually? And the answer is, of course, no. Flags will do this for us. Flags is the neural network library based on JAX. And Flags will handle this job that I showed you here manually in magnificent beauty. But this is now the job for the next video. I hope you have now an idea, if we compare PyTorch 2 and JAX and flags, why here when we go now from PyTorch to JAX, and we have here all those parameters that we must manually feed in and feed out. And please have a look here. Where's my function? Here, you see here my update function. Have a look here. We have here the parameters we feed in more or less manually. And then we feed out the new parameters here also. So this is something that we hope that the next library flags will do for us. And we will have a much more elegant solution. And this I will show you in one of my next videos. I say I hope you enjoyed it, and I see you in my next one.